and welcome to our breakout session on Nexus 9000, a brief architecture and troubleshooting session. My name is Sridhar Dhodapkar. I work for Cisco Service and have 15 plus years of experience. Main job responsibility is to resolve complex network issues, work very closely with the engineering team, and also provide technical training to the worldwide TAC. We also have one of my senior colleague, Sukumar Subbaran. He's a distinguished engineer from Nexus 9000 engineering team. He's been helping me and guiding me to build this whole content. So we have quite a bit of content and very interesting information to present. So the session goal, correct? It's very straightforward. I'm going to cover basic blocks of the switching, which would help us to understand the different troubleshooting scenarios. We will also introduce you to system telemetry. What are the tools available on this platform? What I won't be covering here is the NXOS architecture or any other Nexus platform. These are some of the related sessions. You can, for sure, need to attend Nexus 9000 architecture, which is, I believe, is another 2-hour session. Nexus OS software architecture, because that's going to be pretty much common for different platforms running the NXOS. And if interested, something about the Nexus 7000. So when I saw first time the email coming from the CiscoLive team, I thought, let's do something different this time. Let's try to build a nice troubleshooting session for our customer, something similar to what we do day in, day out. So with that said, I went to engineering team and started talking to Sukumar. Sukumar jokingly said, hey, why you want to create a troubleshooting session? There is not going to be any trouble in our product. We'll make sure it will be all fully tested and launched on the site. I know he was joking, so I said, okay, let me rephrase. Let's build some material, some content, and try to share our knowledge, our experience with our customers, so it will help them to rule out Nexus 9000 as a source of problem. He said, yeah, now you're talking. So then, I got a lot of help from the engineering and started, building the agenda. Everybody was excited. Hey, let's do unicast, multicast, VPC, QoS, VXLAN, layer 1 issue, layer 2 issue. I said, wait. I can only accomplish and deliver very little information in 2 hours. So we did some brainstorm session and basically went over the service request opened by our all customers. And then figured it out, what is the immediate need? What exactly our customer really looking for? So based on that, we came up with this agenda. So obviously, as I said, I need to cover a few main blocks from the architecture perspective, because without that, it would be a little bit challenging for me to explain the troubleshooting tools and etc. Then we will get into the system health check telemetry. We'll introduce you to the different tools available on Nexus 9K. And then we will get into the different case scenarios from the troubleshooting perspective. And at the last but not least, we will go over some of the goodies, some of the nice things on this particular platform, and also some 9K related specific limitations. One more thing I want to mention here. So this is an advanced session. And when I build this content and then send it for the review, I got pretty much the same type of feedback. The material is good, flow is good, but you need to be cautious about the time. Since I have a lot of material to present, and if at all you happen to have some questions, I would request you to use the online tool. And I have Steven and Carlo, who are our question manager, along with the Sukumar. They would try to answer as much as possible. If not, we can also take offline. One more thing. Again, this is some material which generally we try to give to the technical support team members. So for some, it might be just what they are looking for. And for some, it may be not enough. They probably need some more information. And for somebody, it might be just dry. And on top of that, they have to listen to a person who has a tendency to talk fast with a heavy accent. But I don't blame anybody. I will do my level best, to control my speed and then try to, make this session as helpful as possible for everybody. So it's a known fact now. Nexus 9000 is the industry's leading product, which basically provide you 1, 10, 40, and now 100 gig Ethernet interface for your data center requirement. It's basically built using the merchant silicon, and we will get into in the session, and you will understand what I mean by the merchant silicon. So this is how the modular chassis look. It has some of the main components like supervisory card, fabric module, line card, system controller, fan tray, power supply. So other than the power supply and the fan tray, pretty much everybody has something called OBFL, onboard failure logging. What it does, it is some sort of like a black box. It keeps monitoring and recording any anomaly which this particular box is going to encounter. And it's just going to store it, and it can be basically used for any failure analysis. Of course, the first FRU is the supervisor module. We have a high-speed multi-core CPU with a very large memory, and then control, and it provides the very strong and reliable foundation for the control plane for the switching platform. So in short, the supervisor is responsible to take care about the control plane functionality. It's half in width, which means one single slot can accommodate active and the standby supervisor. The next in line is the system controller. So the system controllers, the main job is to host 2 communication channels between supervisor card and the line card and the fabric module. Basically, to do certain internal system management. Other than that, it would also take care about the power supply, fan trays. So some of this functionality has been offloaded from the SOUP card and is being given to the system controller. So just SOUP card is allowed to do focus on some of the very critical functionality. Of course, we have a variety of flavors of line cards. Some of them are built using merchant silicon, and some of them are built using merchant silicon plus homegrown ASIC. So when I say the merchant silicon, we call it NFE, Network Forwarding Engine. He has the main responsibility of making the forwarding decision, which means he needs to have quite a few number of tables to store some of the information like MAC address, IP host table, and certain TCAMs for the ACLs, and buffering for the queuing. So all that things is a part of the NFE. We also call it as a T2. So and you might be hearing me using these terms interchangeably. But at the end of the day, NFE, Network Forwarding Engine, is same as T2. And then the homegrown ASIC, we called it the Application Leaf Engine. It's called North Star. I will try to stick to the term T2 and NS. Okay, but as you know, once I get into my flow, I might start interchanging these terms, or I might use both the terms. But end of the day, NFE is a T2, and then the ALE is a North Star. So on the right-hand side, we have the block diagram of the line card, one of the line card. And in the miscellaneous sections, we have provided you block diagrams for most of the other line cards available today. So as you can see, these two T2s are, the Trident 2s are basically serving your front-end port. And in the back, they have the North Star. One more term is basically called a high gig. So You will also see me mentioning a lot of things about the high gig. So high gig is nothing but the internal interfaces. They are not visible from outside. These are either the 40 gig links between the T2 and the North Star, or from the line card to the fabric module. And the North Star, or if the line card just have the T2, they would just go connect to the 6 fabric module. Every chassis would have the maximum it can accommodate the 6 fabric modules. Fabric module. Yep, it looks very straightforward. Yeah, its basically job is to interconnect the line card. But look at this. I don't know whether you have noticed or not, but if you really look at the chassis, there's no backplane. And when I found that there is no backplane, I was very happy, because in the past, I had troubleshot quite a few number of issues around the intermittent packet drops, and eventually they were root cause to a bad pin or the bent pin on a backplane. So when I found that there is no backplane, I thought one less issue to worry about. So fabric module will provide you 320 gig per slot. Another very important thing, fabric card will also have T2, which is the NFE, which means they will also contribute in making certain forwarding decision. And you will learn that in my subsequent slides. One quick thing which I want to highlight here is that if at all you happen to have just the 3 fabric module, for whatever reason, make sure they are installed. They are installed in an even slot, because the fan trays which are sitting behind this fabric module draws the power through a connector which goes through this even slot. So if the fabric module is missing, the fan tray behind that might not function. It's not a bad hardware. It's not a dead fan tray. It's just not getting the power. This is the overall block diagram of how the chassis looks. Now let's move to the fixed configuration switches. So we have like a fixed configuration switches called the Nexus 9300 series. So they have something called GEM module, Gigabit Expansion Module. And that module need to be present to bring up the system. If that module is not present or is badly seated, the system won't simply come up. So please make sure that first thing is that yes, it is present, and the second thing is that it is properly seated. Now these GEM modules, we can have 100 gig interfaces also. This is one of the simplest block diagram I have ever come across about any platform. Very straightforward, correct? We have a Trident 2, T2, serving the front end ports. It could be 1/10 or whatever it is. And in the back, it goes to the North Star, and North Star is basically serves the 40 gig ports, which you see on the GEM module. So I thought, this probably might be covered very well in some of the other architecture section, but I thought it's very important for me to talk about here, because if I don't understand how a unicast packet would get switched inside a system, I won't be able to start troubleshooting a unicast packet drop issue. So I thought let me spend a couple of minutes here and then go over how a given packet would switch inside a system. So when packet enters the line card, the first thing it does, it parses the first 128 bytes, and it's nothing but it's in the header information, correct? And in header, what we have? Source IP, destination IP, source MAC, destination MAC, ether type, TCP protocol type. All that information is required to make a forwarding decision. So I'm going to show you this whole packet flow, first talking about the ingress pipeline and then the egress pipeline. So as and when the packet is getting processed for the ingress pipeline, it is subjected for the L2 and L3 lookup. So when the packet enters the line card, the NFE or the T2 would look into the destination MAC. And if the destination MAC is a router MAC, it might be HSRP MAC, then it gets qualified for the layer 3 switching. However, if the destination MAC is not a router MAC, then it gets qualified for the layer 2 switching. And as a part of the layer 2 switching, the source MAC of the incoming packet, source MAC of an incoming packet is also looked at it, and if it is already not learned, the system will learn it and accordingly update the layer 2 table. For the layer 3 routing, the destination IP is considered, and it is searched in a table which is on T2 called L3 host table. It is nothing but the /32 entries, which means the ARP has been resolved and then adjacency has been programmed. So that's the information would be there in the layer 3 host table. And if there is a hit, it's going to make all the forwarding decision. With respect to it will provide you the rewrite MAC address, decrement the TTL. It will tell you, hey, this is your egress module where you need to exit. On that egress module, this is the particular port you need to exit. So all that decision would be taken care here. So as and when, at the same time, the packet is also subjected for the ingress ACL. And depending upon the ingress ACL, either the packet would get dropped or the forwarded. And then the packet is handed over for the traffic classification. So the traffic gets classified based on a different QS level. And after that, there is an ingress policing, which is also part of the ingress pipeline. That tells me that every T2 on every line card, there is a control plane policer. After that, the packet is handed over to the fabric module, because now it needs to go to the egress line card. Now, when the packet is received by the fabric module, it's going to look and then see if the forwarding decision has already been made. If it's already been made, it will honor it and accordingly push the packet to the egress line card. Now, for whatever reason that decision is yet to be made, for example, when on the line card, when the NFE was trying to look for the L3 host IP address, there was a miss. Then the fabric module is going to try to make a forwarding decision based on the longest prefix match, which is nothing but the subnets. So this might be something like the destination IP is not directly connected. You need to have a couple of hops. So the forwarding decision would be made based on the subnet. And obviously, then he would also provide you the rewrite MAC address, decremented TTL, egress line card, egress port, etc. So after that, it's an egress pipeline. According to me, the egress pipeline is pretty simple compared to the ingress pipeline because most of the complicated or required decisions already been taken care. So the only one thing which is most important here, obviously, other than the egress ACL, is the buffering. If there is any congestion on the egress path, the packet actually get buffered on the egress line card. There is no virtual queues. So if at all you are seeing some kind of packet drops in the egress direction and you are suspecting something is wrong or maybe the buffers are overutilized, egress line is where you probably want to really check at it. And again, as I said, the packet would get processed for the egress ACL, and depending upon it, whether its decision, it would get forwarded or the drop. And once let's assume that it's the packet is allowed to exit, then the packet modification will take place and the packet is shipped outside of the chassis. So this is the flow, and I thought it would be really interesting to explain because now if you are troubleshooting a unicast packet drop issue for the layer 3 host, then you know the forwarding decision is made by the ingress line card, and you need to use all those fancy commands on the ingress line card because he's going to make a forwarding decision. And if it was not the line card and if the decisions are made because of the longest prefix match, then you have to go and then troubleshoot in the fabric module. Any buffer congestion or on the egress line card. There are a few more things which I'm going to talk about it. And the first one would be unified forwarding table. And this is also, understanding of this is also very important to understand some of our troubleshooting tools and then troubleshooting scenarios. So T2 uses a combination of dedicated TCAM along with the shared hash table memory, and it's basically to store the layer 2 and layer 3 forwarding information. We call it as a unified forwarding table. It's a flexible table, which means I can divide that table the way I want as per my network traffic requirement. So this This space basically is divided into 3 different tables. First, one for the layer 2 MAC address, second one for the L3 host, and third one for the longest prefix match. And now, depending upon the mode in which the T2 is allowed to come up at the time of the system bring up, the respective space is allocated to each table. So for example, let's say when you bring up your system first time, the T2 on the line card is in the mode 3, which is the default. So then, in that case, it will make sure that for the L2 on the line card, we will assign the 98K space. L3 host will get 122K, and the longest prefix match, which is for the subnet, would get 16K. For Nexus 9300, we just have 2 modes. The default is a 3, and then you can change it to the 4, where that you want to have a bigger space allocated to the longest prefix match and not to the L3 host table. And this is how I was just displaying here how you can basically check in what mode we are running and what are the utilization of this particular table. On the chassis, it is little bit have more choice because of the fact that there is a fabric module. And as I mentioned, the fabric module does contribute into making a forwarding decision. So again, based on your traffic pattern, either you can stick to the default system routing mode, where I just said the line card is in the mode 3, and then the fabric module is in the mode 4, because fabric module, we try to put all the longest prefix match entries in the fabric module, so it needs a bigger space. Now, you might think that, okay, my traffic pattern in such a way that I don't want my fabric module to make any forwarding decision. Let the whole line card do that. Yeah, you go and then change the mode to the non-hierarchical mode, where basically everything will be on the line card and nothing will be on the FM. So I'm just showing you this, how the whole utilization table would look if you get into that mode. As you can see, that for the line card 1, which is the slot number 1 is for the line card, we have assigned the table space to store all this layer 3 information. However, the mod 21, which is assigned to the fabric module, it is 0. ACL for the TCAM. There are 2 TCAMs, one for the ingress, one for the egress. For the ingress side, we have a 4K TCAM, and for the egress, there is only 1K. And there are different banks with the different sizes. There are certain types of ACL which would need a double width. For example, MAC, IPv6, and certain QoS thing. WACL would also need a space from ingress and the egress. So if at all if you want to configure WACLs, then make sure that you have the space not only in the ingress VLAN, but on the ingress TCAM, but also on the egress TCAM, because WACLs are directionless, correct? Quick table just to help all of you to what is the default carving when you bring the system first time. So you may see that there are certain features which we don't allocate any TCAM space. So for example, let's say that all of a sudden we want to configure a port-based ACL. There is no space allocated to it. So then I have to free up certain space from certain other features and assign to it. And this is how I will do it. This is the way I can find out, okay, what is the current carving, or how are the different features are getting different sizes. And if I want to make some modification, this is the way to go. And it will need a reload. If it's the line card, you need to reload the line card. If it is a TOR, you need to reload the TOR, because we are just recarving or the hardware resources. The third thing, buffer and the queuing. So let's talk about the Trident 2 first. So we have 12 megabytes of the buffer shared by all the ports for all traffic in both directions. This particular buffer is actually divided into 2 service pools. One control and the other is default. Default is any traffic, control is the control plane traffic. However, if the line card is built using merchant and the homegrown ASIC, which is a North Star, then the same shared buffer is divided into 3 pools. Control, default, and out of band flow control for the unicast. Why we need that? We need that to monitor or signal the North Star to slow down sending traffic to T2 in case of there is an egress congestion. So that signaling would need some space to do that kind of monitoring, and it will be clear in next slide. So now going to the North Star, we have a bigger shared buffer, which is of 40 meg. And again, it's divided into 3 service pool controls. We have one specific pool for the span, and then there is obviously the default. But if you really look at on the left-hand side, out of the 40 meg, 10 MB buffer is reserved for the traffic going outside the North Star toward the fabric module, if North Star is on the line card. And if it is a part of the TOR, that is 9300 series, then that traffic would be going to your spine. The 20 MB buffer is reserved for the traffic which is coming from the fabric card to the line card, if it is a chassis, or coming from the spine to the TOR, if it is a TOR. And then 10 meg buffer is for the hairpin traffic. So let's talk about what is that hairpin traffic, why we need to reserve the 10 MB for that hairpin traffic. So we have a feature called buffer boost, which is enabled by default. So what it is going to do is, now you all heard that on the T2, you just have 12 megabytes of buffer, and there is a possibility of a traffic pattern where it is coming on 10 gig and exiting on the 1 gig. And that particular pattern might run out of the buffer. So then it gets the privilege to access that extra 10 meg buffer which is on the North Star. So if the buffer boost is enabled, then the traffic in this condition would be actually sent to the North Star and take the advantage of that extra buffer. And if you disable it, it's just going to go locally on the T2. Make sense? All right. So quick recap. So we quickly understood the main blocks of the switch. We understood, or we went over the unicast packet flow inside a chassis. We spoke about different tables, ACL, and then the buffers. Now let's quickly move into the system health check telemetry. So if I'm in charge of my data center, there are a few questions which keeps bothering me. The first thing is that, hey, is my system performing up to the speed? Or what is the baseline of the hardware resources? How much is the CPU utilized? How is the memory utilized? How are my TCAM's utilization looks like? So these are all the questions. So keeping, and again, this is the way where you can proactively try to avoid a problem instead of waiting for it to, blow up. So we have quite a few number of things which you can monitor. And some of them are very straightforward, so I'm not going to go over this. They are there in the hidden slides. So the PDF which you are going to get it will have all the information. I want to emphasize on 2 points here. We, as a Cisco, takes a lot of efforts. There's a lot of testing we conduct to provide this recommendation, which is the recommendation for the NXOS, and also the scalability number. How many OSPF peers you want, how many VPC you can configure. So there's a lot of testing goes in the background, and this information, we publish it for all our customers, and I want all of you to take advantage of it. So I would say that it is always better to go and then check if my data center is running up to the right code. Of course, the most important resources are the CPU and the memory. Yep, we have a high-speed multi-core CPU with a very larger memory, but once in a while we might see some anomaly, correct? Is CPU spiking once in a while is a problem? No, it's not a problem. What is problem is if certain process spikes up and stays there, it just hogs, it's not going to release the CPU cycle, that is a problem. But once in a while, if it spikes, yeah, some process needs some CPU cycle, yeah, it's free, it's going to take it. And of course, once it's done, it's going to release it back. So this is a very cool command where you can just get the whole resources for the CPU and the memory. The one thing which I want to highlight here is that make sure that the current memory status always looks okay. Also, you can monitor the memory utilization on the line cards. So it's just not on the supervisory card. And at the last, if there are any anomalies, it will get into the log. And you can check if there are any alert logs. Technically speaking, when I use this command, I should see blank output, which means we didn't see any anomaly, which is good, correct? If you see something, call us. Today, I see that there are a lot of our users who have very strong Linux background. And they want to use certain tools which are available on the Linux to troubleshoot the switching problem also. So here we go. You can use the top command, which basically provides an ongoing look of a processor active in real time. You just need to get into run the bash and then run the top command. And as I said, it's an ongoing look at the processor activity. So next thing is about the sockets. We all know that the different processes would communicate with each other using TCP and UDP and eventually would use the socket. And if these sockets are seeing any errors or any drops, that would cause certain anomaly. So please monitor that. And if you see these numbers incrementing, then something we need to investigate, correct? So MTS, it's a message and transaction service. So what happens is there are two processors, say for example, OSPF gets an update. There's a route change. Now it needs to communicate to the other processes so that that information eventually get programmed in the hardware. So for this is the process, we call it the message and transaction services. And now what happens is these two processes, when they want to talk to each other, they would use a shared buffer. And again, we don't want to have a leaky boat, correct? We don't have to have a leak in those buffers. So if you really want to monitor that, you can use this particular command, and then it basically should, you should see that not a single, this number should be incrementing in both direction. Yeah, whenever there is an exchange of the messages taking place, yeah, you will see certain numbers in the queue, but once they are dequeued, that should disappear. But if you see this keeping building up, yes, that's the problem. So for example here, in this case, the SAP number 320 was actually owned by the OSPF. He learned some route change. It wanted to update to the other processor so that change would get programmed into the hardware, and it's just trying to send that information, and it's just getting queued. It's not getting dequeued. So that might result into high CPU or unstable routing table. So if you see these kind of things, yes, we need to investigate. End of the day, this buffer should never be leaked. So supervisor card, as I mentioned while talking about the system controller, correct? So actually the supervisor card keep checking the health of the line card on the fabric module. And they do it by sending some heartbeat messages. So these heartbeat messages can get dropped, or they might see some error on the channel. So it's not the line card which has sending the heartbeat messages in a problem, but something is wrong on the channel. That might just raise a false positive thing, and that may kick in the recovery mechanism. We want to avoid that. So keep monitoring this channel and then make sure there are no errors, drops, or overruns. So again, the EOBC and the EMON, which is EOBC and then the Ethernet protocol channel, are monitored. And if there are any heartbeats coming from the line card, then the supervisory card would take an action to recover that line card of the fabric model. So in this case, This was for the fabric module where we were seeing the heartbeat missing. And the supervisor need to see that, okay, there are certain number of heartbeats miss in certain amount of time. So if I recollect this number very well, I think it is they need to see the 8 drops in 800 milliseconds. So if that happens in that duration of time, then only the recovery mechanism will kick in. So end of the day, you should never see a heartbeat missing coming from the line card or the fabric module. So we spoke about the buffers, correct? The T2 buffer and then the North Star. We actually go and then monitor this buffer utilization at very aggressive rate. As a matter of fact, in the latest code, these buffers will get pulled after every 500 milliseconds. And if the utilization crosses 80%, a message will be logged. So this is a cool command where basically, it will give me the answers. Hey, how much is out of that 12 meg we are assigning to the control traffic? So the SP3 is basically nothing but the control plane pool, and there we are assigning this is the actual site. And here, it's getting built up, which is not good. So technically speaking, when in a healthy system, when you are using this particular command, these total instance usage should be bare minimum or technically 0. Of course, there is a similar way of polling this information for the North Star also, and then you can poll this information for the traffic going out of the system and then coming to the system. We all know why we need control plane policer, correct? So the way we implement is that we classify the interesting traffic and put into the different buckets, and then allow it to leak at certain rate to the CPU. Just want to make sure that we don't overwhelm the CPU. Straightforward, correct? So, of course, when you are monitoring the statistics of the control plane policer, you should never see a drops on any class. And if you are seeing any drops in any class, we must go and investigate. Maybe it probably just need a bigger bandwidth, bigger rate, or there is something, there is not a legitimate traffic which is getting classified in a given bucket. Now, seeing drops in a default class is okay. Okay, because whatever doesn't get classified into all other classification, we would put it in the default. But if that drops are really incrementing at a very high rate, I would go and then investigate that.
What's considered very high?
Defaulting, and you have to keep monitoring it. You need to have the baseline, correct? Right. Yeah, that's the whole purpose, correct? Because that's exactly the thing, correct? I don't know what are my historic numbers. So the question was, what's the high rate for the default thing? And that's the reason, we are trying to pitch in here saying that keep monitoring this thing so you know what is the baseline for the things. When you are building up your data center for the first time, bringing up the things, we recommend you to stick to the strict COP, and then you can tune it depending upon the way you want it, depending upon your application traffic. Why I'm talking about this slide here? I already spoke about the COP, why I need to, again, have one more slide. The reason here is that on the Nexus 9000, we are trying to get every traffic classified and then rate limited under the COP. And some of this traffic which you see here are basically hardware rate limited on the other platform. But on the Nexus 9K, we're trying to get as much as possible under a single umbrella so that you don't have to look into too many different places. Does that mean that we don't have the hardware related limiter? No, we do. Because there are certain processes which actually runs on the line card CPU, for example, BFD. They won't be sent to the CPU of the soup. So they need to be tracked there itself. And there could be some instances where not all traffic would get classified by the COP, so we have an extra check here. So now we have in a system the line card, and obviously there are the 6 fabric modules on any given chassis. And traffic would need to cross the fabric module when it needs to go from one line card to another line card. And those are the internal ports. How are they utilized? Are they overutilized? Is there something problem? So to get a utilization number, we have this one particular command where it would go and then read the statistics of the internal ports, which are basically going from line card to the fabric modules. And it would provide you what is the utilization in the TX direction and the RX direction. It might just help you to design, help you to place your servers in certain places, depending upon the utilization, just a data point. Now, there are a lot of issues when it comes to what software is telling and versus what hardware is understanding, or it could be vice versa. And for example, in the routing table, it says that, hey, to reach destination C, go to your next hop is B. And then the hardware is saying that, okay, to go to C, go to Z, or it might not even have that route. Right? We have a way to troubleshoot these kind of issues. But what if we give you one just tool, basically, which would just go and then check if there is any inconsistency between what the software is thinking and what the hardware is thinking, or vice versa. This is just one example. So we have similar kind of check to check the VLAN table, to check the spanning tree status, to check the members of the port channel. You don't need to really get into the T2 and then really check the hardware and then compare it with the software. The MAC address table. Many times we see that the software know that certain MAC address is learned, say for example, on 1/1, but the hardware doesn't have that information. And we all know the traffic gets switched in the hardware. So when the packet comes, it will just get flooded. A quick way to identify this inconsistency, you can just run this command and then identify the inconsistency. Unicast forwarding consistency checkers are a little different. First, you need to invoke them and then test it. So, first I will start the consistency checker for the forwarding and then basically check the status. And if it is passed, there is no inconsistency. And in spite of that, if you still have some doubts, then of course we have in detail troubleshooting scenarios. Now, one point here I want to mention is that if I run this consistency checker when the routing table is continuously getting updated, it's going to show some inconsistency because software is still in the process of giving that information to the hardware and vice versa, correct? So don't get panic or misled if you are really running this particular command when your network is still trying to converge. And it's true for the even MAC address. If we have a spanning tree loop or some spanning tree is reconverging, yeah, we are going to flush the MAC address. And during that time, if you run this consistency, there could be some inconsistent things because they are not yet done in updating the hardware table. Gold, very important thing, correct? Generic online diagnostics. We have so many DIAGs, and every day and day by day, we are enhancing this. So if there are any anomaly, just catch it there itself. The most important thing about the rewrite engine loopback. We can run these DIAGs on demand. All right. So let's jump into the troubleshoot toolkit. So initially I thought that all these tools, I can actually use it while talking about the case, different case, correct? But here's the thing, correct? I have one tool, not necessarily it has only fixed usage. It can be used in a different way, correct? So I thought, okay, let's go over the different tools available. And then when I talk about the case studies, I can just point out, hey, this is what you can do here. This is a tool which you can use to get the right information. This is something which we have for a while, Ether Analyzer. The main thing here is that it should be used to troubleshoot or to understand the traffic pattern which is going to the CPU or coming from the CPU. If the traffic is switched in the hardware, like for example, if it's entering, say, 1/1 and exiting on 10/1 or whatever it is, that time this tool cannot be used. So it is basically to, to use a traffic which is coming from outside, and it's an interesting traffic which need to seen by the CPU. It could be a OSPF hello packet, and for some reason, we want to confirm that whether it is all the way making it to the CPU of the SOUP card or not. So that's where I will use it. It's based on the Wireshark, so most of the filters, display filters and the capture filters will work. Again, as I mentioned some time back, there are a lot of users who have a very strong Linux background, and they just want to use the tools available on the Linux. So TCP dump, just make sure that you have enabled the feature called bash, and once you do that, invoke the bash, and log in there as a super user, as a root, and then you can use the TCP dump command the way you otherwise would use on any other gear running the Linux. ELAM. This was something was introduced probably 10 years back with the SOUP 2 on the 6500, SOUP 720. But on the Nexus 9000, and again, this is the tool which actually would help you to capture one packet which is switched in the hardware. So it's a trigger base. So you set up a trigger. For example, you want to find out the packet is coming on the 1/1. Is it going to leave the 10/1? So that trigger, you can set it up and then get the result. It will tell you, yeah, it came in, and now here is where it is going to get switched out. And you validate that with your understanding of the packet flow. Now, this is only available on the line card, which has a North Star, because ELAM is something which Cisco built it. So it will be only available on the ASICs, which are homegrown ASICs. So on the Nexus 7K or the 6500, we had Earl 7.5, Earl 8. It's all Cisco ASICs. So we had the privilege or liberty to have that there. But on the Nexus 9000, the T2 actually don't belong to us. So the only where you have the ELAM is on the North Star. So are you telling me that, okay. So before moving further, I really want to familiarize you with something called ingress and the egress direction. So basically, when I started playing with this particular tool, I was not able to capture the traffic. And then later on, I realized that, hey, I'm actually using a wrong direction, because the flow of the packet, which was what I was thinking is right, is not the same what the North Star would think. So it's very straightforward. If the traffic is entering from the fabric module, if it is a chassis, to a line card, which has a North Star, then it is egress pipeline. And on the TOR, if the packet is entering from the spine on the GEM module, which has the 40 gig, obviously those 40 gigs are supported on the North Star, then it is the egress pipeline. So you have to just follow this direction and then use this keyword so that you will capture the right packet. And if the traffic is entering the North Star from the T2, which means the traffic is coming from the front end port, cross the T2 and goes to the North Star and then exit towards the fabric module, then it is the ingress pipeline. And in case of the TOR, this traffic would go from the TOR towards the spine. Very simple steps. You have to attach to the mod and initialize the ELAM process, set up the trigger, start, and if it catches the packet, you would see the status as triggered. And it's going to display you, and when you type the report, it's going to display you a lot of information in hexadecimal. So you may just want to go and then verify the source IP, destination IP, source MAC, destination MAC, TTLs and all that kind of stuff. So when I was talking about the ELAM, I said that it is available only on the North Star. So you can only capture or validate the traffic coming in if the line card has a North Star. So are we out of luck if I have a line card with the T2 or, no. So we have another tool. It's called as a packet tracer. So it's in the simple way, it basically, what it does, it allows you to set up an access list. And once you do that, it will get programmed on all the line card fabric module, wherever the T2 is there, and obviously T2 is there everywhere. And once it gets programmed there, if it sees that particular traffic coming which matches that access list, it will start counting the packet. So at least we know that the traffic which you are trying to troubleshoot, either is it coming to the box or if it is not, and if it come in, on which line card, which in the front-end port it is coming in, did it seen by the fabric module or not? So all that kind of answers, you will get it using the packet tracer. It is only in the in direction, that means the traffic coming in the Trident from whichever direction will be captured. This is how I would use it. First, configure the filter using the test packet command, start, stop, and then show, and then it basically would show you certain output, which I'm going to show you in the next slide. So two options here, detail FP and detail HG. What does this mean? So when I use the detail FP keyword, it will actually give me the front panel port. So I know that, okay, so-and-so packet is entering on so-and-so line card on so-and-so interface. And HG would tell me that the high gig port, which is the internal port. So if you want to know which internal port it is coming in, then use the detail HG option. Yes, so hold on to that thing. That's a very good question. Every my troubleshooting scenarios, I would take you to the Broadcom shell. Okay? So stay tuned with me. All right. So once you configure the filter, as I mentioned, correct, it would basically tell you if there is a hit for that access list, and it would give you which physical port it is coming in. And now this physical port which it's going to give is an internal port number, which we just need to map it to the actual front-end port number, and then I am displaying the command, which would help you to just convert that information. Another tool, flex counter. It basically helps you to count the number of packet hit to a given agency. It's a very simple tool, but at least you can say that, hey, the packet came in. It looks like my NF is making the right decision because it is hitting the right agency which it's supposed to switch out of the system. So this is how I would configure it. It's just one single command: test hardware internal agency for the next hop, and just do it enable. And after that, you do show, and it would just give you how many packets were hitting that agency. Skip this. So when you go back and then look into PDF, you probably would get a question saying that, hey, why I'm seeing these counters only for the mod 21, and why we didn't see it for the slot line card. So the answer to that would be that the IP route which I was trying to capture was not an hit on the line card. So and that traffic to that particular route was used by FM to forward the packet. Okay, so let's get into the Nexus 9000 troubleshooting, and here where I would talk more about the Broadcom. Okay, this is the one slide. If you understand this, I think most of the things would be straightforward. Okay, so every line card need to have a T2, which basically responsible for making a forwarding decision. And the basic question is that, okay, I have this water line card, how many forwarding engines it has it, correct? So to get that information, use this Broadcom shell command for the given module and just say show unit, and it will display you the number of units. So in this case, the given line card which I'm displaying here has a 2 T2s. Okay, that's a good information. Now the second question comes to my mind is that, okay, that instance 0, the first T2 which I call it instance 0, or the second T2 is instance 1, what are the different ports which goes to, what are the different ports which goes to the front panel, and what are the ports which goes to the internal side, correct? And that answer I can find out by using another Broadcom shell command called PS. It's just a port status. So when I type that, it's basically, so this is the information which I am getting for the mod 1 instance 0, which means this is the T2 instance, okay? And now once I type that, it's going to list all these internal interfaces. Some of them are called as a high gig interface, and some of them are called as the XC interface. So the XC interfaces are those which comes to the front side. These are what you would see and where you would connect your servers. And then again, I mentioned high gig interfaces are the internal interfaces. So this gives you a lot of information, correct? It gives you if that particular link is up, and what is the speed, and etc. And these are 0 base. So technically speaking, Ethernet 1/1 would get mapped to XC0. So instance 0, XC0 is Ethernet 1/1. Instance 0, Ethernet XC11 is the Ethernet 1/12. Instance 1, which is the XC0, is Ethernet 1/13, and so on and so forth. Okay. Some of the common issues. I'm installing the transceivers, and it's basically has not been recognized, correct? So if that is what is happening, you can just get certain BCM event history, the Broadcom event history, and it should give you some information. If it's not user friendly, just call us, and then we will try to decode that for you. But that's the command which you would find all the event history of a given physical interface, and it would help you to get an answer why the certain transceivers are not being recognized. Of course, I want to see, is my interface is been set for the right MTU? How is the speed? Flow control. I might have, from the software perspective, I might have set the MTU to 9K. Does the hardware also knows about it? So these are some of the things which would help you to get that answer. Interface drops. So if you really look at the interface drops, it is like a catch-all into single bucket. And it might sometimes confuse us, saying that, okay, what exactly these drops are. And if you really want to get more detail about that, you can use the Broadcom command cstat, the counter stat, for a given port. Again, I just want to emphasize here that, correct? So Ethernet 1/30 would be XC29 because that is the 0 base. You should not just get that for the XC30. It would be for the 1/31. And again, these outputs are a little bit cryptic, but there is a help. You can just use the same command, counter stat and info, and what are the counter you are looking for. In this case, I'm looking for VLAN DR, and it is telling me it means the RX VLAN drops. Probably there is a .1Q mismatch, or I'm getting a traffic on the trunk port for a VLAN which does not exist. So I need to drop it. Fabric connectivity, correct? So we already know if traffic enters one line card, need to go to other line card, it need to go over the fabric module. And then, which means that I need to identify how is the condition of the link going from the fabric, from the line card to the fabric module, and so on and so forth. So before we get into that, as I mentioned, or probably I didn't mention that we have like 3 types of chassis, correct? The 4 slot, 8 slot, and 16 slot. The fabric module, which gets into the 4 slot chassis, only has 1 T2. If you have a chassis, which is an 8 slot, then those fabric module will have 2 T2s. And for the 16-slot chassis, there are 4 T2s, which means I can't interchange and then use one from the other. All FM actually, participate in forwarding the traffic. If you lose one of the FM, it just you have a little bit of oversubscription. But all the traffics are basically responsible for forwarding this traffic. There are two modes here. One is the full rate mode, and then the second is the oversubscribe mode. The default is the oversubscribe mode. And why do I need to care about it? Correct? I mean, why we need these two modes? So the answer to that is, if in the oversubscribe mode, we will not be able to give you the line rate speed for the packet which are less than 200 bytes. So if you have some traffic pattern, or you have some applications which is very chatty and then always have the packet size less than 200, you might not get a line rate. So are we out of luck? No. You can switch this particular mode to full rate mode. And when you do that, you will get the line rate for the packets from the 64 bytes onwards. Of course, when you do that, it will need a reload. When you do that, you have to also be aware of one fact, that not all the line cards support the full rate mode. So there are certain line cards which will get powered down. And why is that so? Because when we switch to the full rate mode, the T2 on the fabric module has 32 ports, each of 40 gig. It gets reduced to 24 ports. And when that happens, there are certain line cards which needs more high gig ports. They can't operate. So something I want to caution you here. What's the line rate? So this is the rate. I don't know top of my head, but this is what we actually publish. I can get you that numbers after this session. So line rate means that whatever the rate you come in, I will forward the packet outside at the same rate. Is that what you're asking? Or you're looking for the numbers? No, that's not what we're talking. You're talking about the bandwidth. That's not what we are talking here. So if your utilization is 50%, you probably don't need to worry about it. I don't know whether I'm answering your question. If not, we can take it offline. Yeah. No, it's just a sequence. Out of 1 to 32, first 24 ports would be just active. Do you want to add there?
No. What is the question there?
So when we go to from the oversubscribe mode to full rate mode, we fall back from the 32 ports to 24. Is like every other odd port we shut it down? Or?
No, it's the sequential ports. First 24 ports of each two T2s are used. That way we only utilize that first 22 ports.
I was wondering, like on the Nexus, whenever you manipulate the buffer, it's not like can't spread out.
Yeah, that's not true here. Yeah. All right, so when the traffic entering a given line card need to egress on other line card, it has quite a few number of options. There are 6 fabric modules, and obviously a given packet can only take one link. So let's say that the packet is coming on line card 1, need to go on line card 2, it can go to fabric module 1, or it has an option to go to fabric module 2 or fabric module 6, correct? So how the system does that? So there are 2 hashing algorithms. One is called as a RTAG 7, And then the second one is the DLB, dynamic load balancer, which is the default. So in the RTAG7, what happens is when the packet comes on the line card and it need to send it to the egress line card, the way it selects the fabric module is based on the header information of an incoming packet. Based on that, it will say, hey, go to the fabric module 1. And from that onwards, that particular flow will always go to the fabric module 1. In contrast to that, in the DLB, which is the dynamic load balancer, the decision of selecting the fabric module will still based on the header, but at the same time, the system would be monitoring the utilization of the different high gig links, and depending upon that, for the next flow, it will probably switch to other available fabric module. So it's the most optimum way of using all the fabric modules. And that's the default. You can change it if you want it, but I haven't seen any need to do that so far from the field. What is the fabric module policy if it sees some problem with the internal high gig ports? So let's say that there is a single high gig port which fails between the line card and the fabric module. What we do? We basically bring down the fabric module if there is more than one fabric module. Obviously, if it is just one fabric module, we don't want to bring down because whole system will go down. And if there is only one FM, then obviously we'll bring the line card. So the line card, we will try to bring down at the end because we don't want to penalize all the servers on a given line card. So that's the last option which we will take. The next two scenarios are very straightforward. If there are multiple high gig links failure for a single line card, to multiple FM, bring down the line card. It's just straightforward to me, correct? And then the last one is, if there are multiple high gig links failure on a line card to one of the FM, bring down the line card. This is how a given line card would connect to the T2s on the fabric module. Every T2 would have connectivity to every T2 on the fabric module, all the 6 modules. One note again, the 9400 series line card only connects to the 4 fabric module. There is no connection to the slot 10, 21, and 25. So what happens if you have a certain line cards which would have connectivity to all the 6 modules, and then this is the line card which have only connectivity to the 4 modules. And if the traffic need to traverse between these 2 line cards through the FM, then we just use the subset FM. So the system is quite intelligent to know that, okay, if the traffic need to be switched on a line card which is just connected to the 4 fabric module, then only pick up those 4 fabric module and then send traffic to one of the fabric module. And if it doesn't do that, then it's a software issue. 16 slot chassis, as I mentioned, the fabric module has the 4 T2s, but not all the T2s are used. Only the first T2s are used, and for whatever reason, if the chassis, if the FMs are down, out of 6, if let's say there are only 3 FM, then we use all these T2s. The same limitation here, make sure about the 90, if you have the 9500 series card, then we have the same limitation here. And one of the line card, which is the 9636 PQ, is not supported. Okay. Now, there are certain line cards which have built-in mux. It just gives you extra redundancy, and it is not for all the high gig ports. But there are some line cards, certain high gig ports would go to 2 different FM, odd and even and odd and even. So in case of something going wrong with the primary FM, the link would just switch to the other FM. Now, when the traffic is coming in a line card and need to go to the high gig, need to go to the fabric module, it's to me, it's just something like a traffic coming in the one switch going to another switch. So I need to check the health of the link, correct? Now, these links are internal link. So my first challenge is to find out which are the high gig links from the line card and how they are terminated on the different FMs. I need to find end-to-end the high gig interface on this given line card, where it is going and then getting terminated on which FM. So if you want that, very straightforward command, it just say, hey, give me the fabric connectivity for the module 1, and then it will tell you that, okay, from the slot 1, the T2 unit 0, it will go to the fabric module which is in slot 21, and then the FM unit, the T2 unit is 0, and these are the high gig interface number. So now I know that if I want to really check the health of this particular link, I just need to focus in the output of the next command which I'm going to show you. You can also get this mapping from the FM side also, correct? Instead of mod 1, use the module number in which the fabric module is there, and you will get the similar output. So once you understand that, correct, then you can actually read the interface ASIC counters and see if there are any RX drops or any type of drops. Don't get misled by the forward TX drops or the forward RX drops. They could be result of some other issue like ACL. Because of the ACL, things are getting drops or those kind of things. Okay, so you might see those on and off incrementing. So that's not an issue for your traffic pattern. So you should only focus on the packet error RX drops and then the TX drops. When you configure the VLAN on the switch, the spanning tree need to forward that, correct? So this same VLAN should also be forwarded on the internal high gig link. If there is a mismatch, then the traffic in one VLAN will not cross the fabric module and go all the way to the other egress line card. So this is a quick way of checking the the status of internal high gig port. You can use the same PS command. It's showing you that the link is up and the STP status is forwarded. Some few more commands, to find out, what are the physical other interfaces which are part of the same VLAN spanning tree group. And at the last but not least, I understand there are certain business requirements where we can't wait to tag to come and really troubleshoot and get the relevant data. So if you encounter that thing, at least, and you believe that it is something wrong with the fabric, get all these show texts which are completely related to the fabric modules. That would give us some opportunity to root cause the issue and then see if there is anything wrong. Now, let's move to the next session where I'm trying to troubleshoot an OSPF flap issue. And I want to make sure that whatever the OSPF hello is coming in, it is seen by the CPU, correct? As you can see from this diagram, the packet comes in on the line card. So the OSPF packet can get into trouble on the line card itself. Then you have maybe 6 FM, 3 FM, and you need to select only one FM to go to the CPU. So the traffic going to the CPU or the supervisor card would always hash to one of the FM. So I will find out which is that FM and then go and then check the health of that FM. Also the link, the high gig link between the line card to that FM. Then the traffic goes to the system controller. There are some internal switch which basically are used to connect fabric module to the system controller. So I will see the health of those switches and see if there are any drops or errors. Then I will check the interface going to the soup card and make sure there are no drops. And maybe at the end I will use some of the tool like Etheranalyzer or TCP dump to really see if the packet is making all the way through there or not. And same concept goes for the egress path also. Whatever the OSPF packet I'm generating, it would come to the system controller, and not necessarily it will use the same FM. It might be a different FM. Let's say in this case it is using the mod 23 FM, and then I will check the health on those particular modules and the links, and then go to the line card and see. So this is the overall flow of the troubleshooting. So obviously the first thing which I would check is on the line card if there are any drops, and if there are drops, I will investigate them. Some of the commands we already made you aware. So again, as I mentioned, correct, I mean, there are certain drops which is like a catch-all kind of things and then put into same bucket. I would always, recommend you to use certain Broadcom commands and get the more information about that before just, blaming the problem on those particular drops. Instant buffer usage. So we know that, the buffer, we have certain reserved space to take care of the control plane traffic. And now as here in this case, you are seeing that SP3 is building up. It might be an issue. So when you use this command on a healthy system, I would expect to see just 0. The instance usage should be always 0. But in this case, it's building up. It's right now showing as a 2939 cells, and each cell is 204 byte. So that is telling me that something is getting congested, and that might explain why probably the OSP packet is either not seen by the CPU or is been delayed. COP. Every line card has a control plane policer, so make sure the COP is clean. You are not dropping traffic for the class where the OSPF is getting classified. Now, the second thing is that, out of 6 FM, which FM I'm going to use? Because the only one FM is responsible to take this traffic to the CPU. We have a way to identify that FM. We identify that FM in this case, which is showing me to the slot number 21. Now I go to the slot number 21 and then check the COP statistics there. Because that's the FM which is responsible of taking all my control plane traffic to the CPU of the SOUP card. Use the same techniques which we have demonstrated to you while going over the fabric troubleshooting. Identify the edgy ports, and then make sure that none of them are showing any drops. So this is between the line card and the FM. Now, once you cross the FM, the next is the system controller. We have to keep in mind that the traffic which needs to be seen by the SOUP card need to cross the FM and the system controller to reach the SOUP card. So you need to make sure the connectivity between the FM and the system controller is also healthy. So that's the next step which I will use to identify if there is any problem. It will basically tell me which interface of that the internal switch has been used between the fabric module and the system controller. If it is down, that's a problem. It could be a hardware problem. And then there are the counters which would show you incrementing. If they are not incrementing, something to be worried about. And at the last but not least, we come to the SOUP card, correct? On the SOUP card, there are quite a few things which we can check. We will check the CPU MAC, which is nothing but the interface which goes to the CPU, and then you should make sure that there are no drops. If there are some drops, we will need to investigate that. There is another command which will give you so many different errors, like alignment errors, system errors. Make sure they are all zeros. If they are 0, we will need to investigate that, and it might explain you why the OSPF packets are not seen by the SOUP. One more thing which I want to highlight here is about the rate. So this gives you the normal rate and also gives you the peak rate. Make sure that these two rates are coming very close to each other. If you see that peak rate, hitting certain threshold or crossing certain big number, I would investigate that because under normal condition, CPU should not see traffic at a very high rate. Again, because of your business requirement, if you really need to take some drastic action, at least gather some information before you fail out the SOUP or the reload the things. Next, let's quickly go over about the MAC address, the spanning tree, and then the VLAN stuff. Correct? We might need to check that if certain MAC addresses which this switch is learning, it really indeed getting programmed in the hardware or not. And to do that, I would just use a command called L2 show. I think it's not been highlighted in orange, but if you see that L2 show here, that's the way it will read the MAC table from the hardware. And I would be more concerned about this hit bit, which tells me that, okay, the MAC address is present, and when I'm executing this particular command, that was in use. So sometimes we see, we were trying to troubleshoot a network issue, and we believe the MAC address has been learned, but the traffic for that MAC address is not coming up. So in that case, that hit flag won't be there, and then it might be as simple as that the packet never came into the line card. So if we believe that we have the right MAC address and the traffic indeed is coming inside the line card, that hit bit should be there. We can also, validate using the broadcom command, what are the different physical interfaces are assigned to the VLAN 100. So in this output, it's telling me that the VLAN 100 is a regular access port, because it is showing that it's an untagged, and then to that VLAN 100, XC0 is a part of the VLAN 100, and XC0 maps to 6/1 on that given line card. So these are some of the commands which would help you to make sure that the MAC address is learned and it's there in the hardware, and the VLAN has the right physical interface from the spanning tree perspective. Couple of more commands to get into the spanning tree. So here, as you can see, we are just trying to identify that for the Ethernet 6/1, is the VLAN 100 is properly configured from the spanning tree perspective, and is it really forwarding? So in the Nexus 7000 and 6500 days, we used to look into something called the CBL, color block logic, correct? So those kind of information, if you really want to get it on the Broadcom, on the T2, these are the commands which will help you. Now let's move to the unicast L3 forwarding. Now we have already gone through in some of the architecture slide talking about the unified forwarding table, but just a quick recap. On the system, the line card and the fabric module both will contribute in making the forwarding decision. And there will be two cases here. So anyway, so the flow here, if you really want to troubleshoot a layer 3 unicast, is basically obviously check the software table. If the software table is not correct, there is no point in looking into the hardware table. Make sure that you have the ARP and then the agencies information is there. Check the route on the RIB and the FIB. And at the last but not least, check the hardware programming on the line card and FM. And here is what we will be focusing today. So there are two cases, correct? The packet comes in, it hits the /32 host route on the line card, forwarding decision is made by the line card. The second case is the incoming packet missed the 32 host route on the line card. Now the fabric card need to make a forwarding decision based on the longest prefix match. And we'll also cover some ECMP route related troubleshooting also. So in the second case, correct, when the line card have a miss for the given route, then it need to send the packet to the fabric module. And that is done by using a default route. And this default route is not the default route which we configured in the routing table. It is a system default route. So when we look into the layer 3 host table, the system is looking for the destination IP, and there is a miss, then at the end it says that, okay, I don't have this route, go to the fabric module. So that's the default route for that given table to send the packet to the fabric module. Let's take a scenario, let's say that the switch on the left-hand side is trying to reach the switch on the right-hand side. Obviously, when you have a problem, the first thing which you do is the ping, and then it's timing out. Then you do the trace route. You do a trace route, and you figured it out that, the first 9K seems to be dropping the packet, or after that, I'm not able to go to the second 95800 box. The first thing which I would do in this troubleshooting is to make sure that router MAC address is programmed in the hardware. Remember, the NFE would make a decision to whether it need to be layer 3 switch or the layer 2 switch based on the destination MAC. And that destination MAC is the router MAC. It could be your HSRP MAC also. But if it is not present in the hardware, then the packets are not going to send for the layer 3 processing. And the way you would check that is to look into my station TCAM, where we will store all the router MAC address. And if there is a hit, then the packet would get qualified for the layer 3 switch. If this is missing, then you don't need to even go any further. Okay, so the first thing is obviously, I'm looking for the show IP route, and then I see that there is a /32 host entry. The output is clearly saying me that, yeah, you have a /32. That tells me now I need to check the forwarding table on the ingress line card. So the first thing what I would do that, okay, if that particular IP address does really exist in the layer 3 host table from the hardware perspective, and I would run, I will read that L3 table using a Broadcom command, and I will see the hit there, the IP address is there, and it will point out to me an interface index. It will point out to me an index. Now, this is the index where all the rewritten, how the packet need to be forwarded, where it need to be sent, what is the rewrite MAC address, all that information would be there at that index. And that would be in the egress table. So it basically, I go and then look into what is the information I have at that particular index. It is telling me that, yes, you need to use this particular MAC address, which is your rewrite MAC address, and this should match to your show IP ARP or whatever is the next hop. And it would give you the internal port number and the mod numbers. You see the mod number 16, I probably have the 8 slot chassis, there is no 16 mod number 16. So these are like an internal mod number and the port number. And the way I would translate this information to the one which I can read is using the Ethernet program manager. And I know the packet need to exit on the 6/33. So if I say that, hey, what is the internal port number and mod number assigned to this particular physical interface, does that match to whatever I have seen in the egress L3 table, then I'm good. Now, let's talk about the second case. The packet comes in, there is a miss. So when I do a show IP route for destination 13.13.13.10, it's telling me that, hey, you can reach the subnet of that, you can reach the subnet and your next hop is 13.6. This is not a /32 host route. And now this tells me that now I have to go and then look onto the fabric module. So I will quickly go and then check if that particular route exists, that particular hardware, that route exists on the FM. And I run this particular command and I see that particular route exists on the FM. And you should see this route on every other FM, it's just not on one FM. So what if we don't have that system default route installed on the line card? Then even we miss the /32, it's not going to go to the FM. How do I verify that? So that you can verify using this given command. And it's very clearly telling me that, yes, there is a default route, and it's basically destined to the FM, and the packets counter is incrementing. That means, yes, this route has been used. I'm still not satisfied. I want to look into the hardware. Okay, I know the packets are coming on the 6/1. Yeah, it's telling me that, this is a miss in the /32 host table. And these counters are incrementing, but I'm still not very confident about it. then you can go and then learn the same information from the Broadcom shell using the default IP. And there you will see a default route. Again, this is not, let's not get confused, this default route with your routing table default route. This is a system default route, which is just used to punt the packet to the fabric module to make a forwarding decision. And it would again will give me the index number. And on that index number, I would see that it is telling me to go to the mod 100, and mod 100 is assigned to all the FM. So as long as I see this particular entry, I know that the default system default route is present, and whatever is missed by the /32 host, it will be sent to the fabric module. Now I will go to the fabric module and then do the actual troubleshooting. I probably need to do this at least on a couple of fabric module, because every fabric module will have the same programming. So I go and then check that particular subnet, whether it exists or not. Remember, on the fabric module, we switch the packet by looking into the longest prefix match table. So I shouldn't be looking at the host IP address, but should look for the longest prefix match, the subnet. And that subnet should present there, and it will again give me the index number. And at that index, there will be information which would be used to rewrite the packet and ship it out of the system. So as long as this matches, I'm good. So fabric card is making a right forwarding decision. Very common scenarios, correct? I mean, we have every other network which would have the ECMP route. So I thought I should have one slide, to help to understand, how to troubleshoot the similar issue if you have the ECMP route. So in here, pretty much the same steps. The only difference here is that the index number which you see, in case you have the ECMP route, would always start with a 200. That's the first indication that you have the ECMP route, and there is a ECMP flag. And the index number which is given in the L3 table would actually have the physical interface where the packet need to exit. So it's just one extra step. So on the /32 host, we get this index number, and it pretty much gives you how the packet need to be rewritten. But on the ECMP, this particular index would actually point you to the multipath table, and in that table, it would have the layer 3 interface which need to be used to exit the switch. And from here, you can just use the same /32 host entry set of command, the flow of commands to validate the information. The last but not least on this thing, you can use ELAM if they have the North Star. You can use the packet tracer. You can use the flex counter, and you can run the consistency checker. Virtual port channel. So I just thought that I will just have one slide to talk about the virtual port channel, just to set up a stage. So it's basically a port channel built across the multiple chassis. It's basically eliminates the STP block ports and then utilize the links in a better fashion. On the VPC setup, if you have a configuration for the HSRP, there is no concept of standby active here. Both these switches which are configured in the VPC would forward the traffic. But only the active would respond for the ARP and all that kind of stuff. So there are two scenarios here I'm going to cover. Okay, the first scenario would talk about there is a traffic which is been flooded, either it is a broadcast traffic or unknown unicast, and if it cross the MCT link, which is the VPC peer link, and then come here, what are we going to do those packet? And then second is basically what happens if the local leg goes down, how the traffic would get routed. So these are the two scenarios which I am going to talk here, and these are very common scenarios which we see. So this is the config. So I have a SVI configuration 10 and 20 on these both boxes, and again, as I said, yes, one of the box would be HSRP active, other would be standby, but in reality, if the packet comes from the switch 1 and get hashed to the N9K1, that particular box, irrespective of whether it is HSRP active or standby, he will switch it and then send it out. Similarly, if the packet gets hashed to the Nexus N9K2, it's his job to switch the packet and send to the destination. There is a concept of a peer gateway. In the peer gateway, what happens is the packets are basic. The flow of packet does not rely on the ARP. So when I receive the packet, what we do is we just flip the source MAC and destination MAC with each other and then just reply it back, correct? Now that caused some problem. And to avoid that particular problem, we have a feature called peer gateway. In that feature, what happens is the N9K1 would learn the N9K2's router MAC address, and it will flag it as its own MAC address. So if at all it receives the packet because of the hashing, and it is to the N9K2 MAC address, it will still consider it as its own MAC address and make a forwarding decision. So if you configure the peer gateway, remember I have explained you in the unicast table how to check the my station TCAM, where we program all the router MAC address. There I should find my peer's router MAC address in that particular table. So as long as I see it there, I should be fine. So this is the second scenario which I want to talk about here. So here's the case where, you know, there is here's the case where there is some unicast flood or some broadcast traffic coming from the switch A, get hashed to the N9K2, and it crosses the peer link. And when it crosses the peer link, what happens if that 9K1 send it back? It would cause me a loop, correct? So we need to avoid that. So that has been done using VPC manager. We have a mask, and we basically mask those particular ports. We know that this particular traffic is coming on the VPC peer link interface for the same VLAN, which we also know how to reach it. So in that case, I should not forward it. So in this case, it is very clearly telling me that the traffic coming on the 1/1 and 4/1, you should not send it on the 6/20. 4/1 and the 4/1 and the 4/1 and the 6/1 basically are the VPC peer link ports. So this is a quick way. If you happen to see like a MAC addresses flapping on the switch A, and you believe that there is some traffic is being looped, mostly it would be like a unknown unicast flooding or the broadcast, then this is the way where you can make sure that the traffic, the masking is done in the right way, and whatever the traffic is going to enter over the VPC peer link, I'm not going to forward it to the same switch towards the south. Okay. Yes, sir.
On the Nexus 93, do you support the peer link on the 40 gig interface or just on the 10 gig?
We can use on both. So the question was whether we need 40 gig to build the VPC peer link. No, we can use the 10 gig also. There's no restriction. Any line card, you can use it and you can build it. Okay, so another interesting thing here, correct? There could be a situation where the local leg of a VPC may go down for whatever reason. So let's say that traffic on the switch B actually wants to reach some device on the switch A, and when it comes here, you see the local link is down. By design, the Nexus 9K is responsible of switching the traffic. Now it has no other choice, but it has to send on the VPC peer link to the other switch, and then he would switch it. Now, how is this functionality is achieved? It is achieved using something called redirect ACL. So what, in nutshell, it does it, when this situation is encountered, there is a redirect ACL comes into the picture, and it tells that, okay, if the traffic is coming to me, and actually it is destined to a VPC port for which the local leg is down, then just redirect that traffic to the VPC peer link. And sometimes this redirect ACL may not function properly. So how do you validate that? I mean, knowing what it's supposed to react with this kind of failure is a good thing to know, but how do we validate if that is what is happening or not? So that is what I'm going to show you here. So when that thing happened, correct, I spoke about the redirect ACL, and that redirect ACL has a group 57. And in that, when I go and then read that ACL, which is the redirect ACL, it will give me two things: the trunk ID of a VPC which is down, and then the trunk ID of the VPC peer link where the traffic need to be redirected. As long as these two are what as per our expectation, then the ACL redirect is functioning properly. Now this is a little cumbersome way to identify it, correct? I mean, you have to go into Broadcom, you have to read the trunk IDs and so on and so forth. So in a newer code, okay, before I go there, I just want to introduce you to the same command, which is the Ethernet program manager. That will help you to identify the trunk ID of the down interface and then the VPC peer link. So this couple of steps looks a little complicated, correct? You need to really look into the redirect ACL, learn the trunk IDs, and then match it. So what if we just give you one single command? In that, where it will just tell you that, okay, this is the trunk ID for which there was a problem, it went down, and whatever traffic is destined to that trunk ID would go to the trunk ID which belongs to the VPC. So these kind of enhancement also we are keep trying to add in the newer software, and that's one of the reason I also advocate for you guys basically to keep up to date with the NXOS. Because these some of the commands, especially like ELAM and the packet tracers, even this kind of enhancement were not present from the day one. So you really want to take advantage of these commands, yeah, you need to be at the correct software version. All right, so I have a few more slides to go, and they should be quick, because these are simply to make you familiar what are the things, what are the goodies which we have on this particular platform. The first one is email. You can configure your box and make him talk to your mail server, and I, as a TAC engineer, if I request you, hey, can you just quickly send me a show version or show mod, or just give me the output of this Broadcom command, you would be able to just forward that information and attach to the case directly using this particular feature. You don't have to copy it, attach it to the email, and send it to it. As of now, it don't support the show tech, but all other commands which we can quickly want to go over it, it would be just handy. You just go there and then put your SR number, attach at cisco.com. It will be in the service request. Bash. So we have opened the Bash access for everybody, but just use it with the caution. I'm sure there are a lot of people here who have a very strong Linux background, but I would just use it with a little caution, because it actually gives you access to whole operating system. Using something wrong could basically, put the box into in an unstable condition. We went over the Broadcom ASIC shell access in several examples. So we are not hiding access to the Broadcom. If you need to use them for the troubleshooting purpose, it is there. And again, for all of these things, you don't need any extra permission like getting into engineering mode, which we used to do in the past, or loading some other plugin to get access to these kind of things. Nowadays, everybody talks about the scripting. For the people who are interested in Python and all that kind of thing, they can write their own script and get the required information. Quick example here, we are just trying to build a script where we are saying that whatever these SSH sessions which are just there sitting doing nothing, just clear them. Just build a simple script to keep this thing happening in the background. Patching. So we might encounter some software defects, and there are certain software defects for which we really don't need to completely give you a new image. We can give you just the fix, and you can just install that particular patch without reloading or without going through the complete upgrade process. At the last but not least, these are some of these limitations. The one thing which I want to highlight here is a lot of our customers keep asking us about the EPLD upgrade. Hey, do I need to upgrade the EPLD? And our answer is that it's recommended, but it's not mandatory. Whenever you are going to the latest and the greatest software version, you don't necessarily always need to upgrade the EPLD. But if you believe that you are hitting some other software defect because of which you need to upgrade the EPLD, then yeah, please go ahead and upgrade it. The FEX are only supported on the TOR, which basically have the fabric ports, not on the TOR, which has the Ethernet port. And of course, please do go and then check the scalability guide. I personally like it because there are a lot of information from the scalability perspective has been provided there. I done a very sincere efforts in trying to present this information in user-friendly way, and I would really, would like to get your feedback so that we can refine our future sessions. So good feedback is always appreciated, but if there is any constructive feedback, that also I would like to have it so that the future sessions can be further refined and made it, and then we can deliver it as per your requirement. So please complete this online evaluation. And thank you.